Okay, so today we will continue with consideration of point processes, and we will consider the question how we can model or how we can construct point processes with some specific properties for points in them. So last time I want to recall that the one of the main point processes that we constructed was a Poisson point process, and in this process, points were somehow independent. Today I want to try to construct point processes in which particles can be somehow or attract each one another or repel one another. And idea to definition for such processes and for tools how we can try to understand them, how we can investigate them, comes from quantum physics. So I will slightly give idea from it, so don't worry who's not familiar with that. So the idea is that we want to describe a system of particles. So in quantum mechanics, we consider that some particles that we assume to be identical. So this means that we consider them with the same masses, or with and we get the same charge, and so on. And the second assumption that we want to give is that they are indistinguishable. So what does it mean? Assume that at some moment of time we somehow can observe a system of here on picture of 5 particles, and for the next moment of time they somehow moved, but we are not able to say which particles move where. So we cannot label our two particles, so we assume that we just can consider the some properties, in my case location of particles, but we cannot say which particle now in this second moment of time. So who is who here? And under such assumption, what we can say about this quantum system? So in quantum physics, they use a wave function to describe a quantum state of a system. So this is a function with arguments that describe each particle. So each argument here can be mass, location, time, and if we have n particles, so we have here n arguments, and it doesn't matter now what form of wave function could be, but the most important now is that we can consider probabilistic interpretation of wave function, and their absolute value in the square of wave function give us a probability density for measurement of the quantum systems at state x1, xn. So if we want to find our quantum system for this state, there's value give us a probability density, and this is what somehow important for us because we will work with probability of finding points in some states at some position. Now let us come back to assumptions that we give for our quantum system, and I recall that particles are indistinguishable. So actually, if we change the position of particles here on this picture, so if we change particle 1 and particle 2, the probability of this quantum system should be the same. So this means that for wave function, we have such relationship that their square of absolute value does not change under permutation of points of. So here by sigma I denote the permutation of n first numbers. Okay, so now what possibilities we have in this case? So now to describe a system of indistinguishable particles, we have two options. If the wave function is symmetric with respect to permutation, so in this sense we have these relations that for any permutation the wave function remains the same. Or we have another option for wave function in which it is antisymmetric. This means that if we apply a permutation for points, then we will have this relationship where modulus of sigma means a sign of permutation. Okay, so since we have two possibilities here, and these two possibilities actually give us two classes of particles. So in the first case and symmetric case, we will have a deal with a system of bosons. And for the second, for the case of antisymmetrical wave function, we will have a system of fermions. And what the most important characteristic for me is that in the first case, in the case of system of bosons, particles somehow attract one another. So this means that they tends to be close to one to another. While in the system of antisymmetrical wave function, here works de Pauli extension exclusion principle, which says that particles cannot be together. They cannot be on the same energy level, so they somehow repel each other. So this idea from quantum physics gives us idea how we can try to construct our point processes with some specific properties. So we want properties with this attraction and with repelling of between our particles. And to have more idea in this case, actually in these two classes, wave a function can be represented in with tools of matrices. So in the case of boson system, the wave function can be represented as a permutation of a specific matrix. Here on matrix, on each cell, we have the covariance between position xi and xj. And for permutation, here I wrote the definition. This is similar to determinant of matrix, but we skip -1 to the power of sign of permutation. So here the summation we have through all permutation of numbers from 1 to n. And for boson systems, wave function corresponds to the permanent of such some matrix. And note it is here that the permanent of a matrix is symmetrical with respect to change of the columns or rows. While in another case, in the case of fermions, in the case of antisymmetrical wave function, it can be represented in using determinant of some of the same matrix. So again, now determinant, I know that you familiar with it, and here we have summation over all products here, over all permutations, and here the difference with the previous case that we have -1 to the sign of permutation. And again, important properties that the determinant of a matrix is antisymmetric with respect to change of rows of the columns. So here, this idea from quantum physics gives us somehow tool how we can try to construct point processes with repelling or with attraction. And now let us come back to point processes. Now we have idea, we can understand what we want and how we can proceed. So now let us come back what we did yesterday. So yesterday we defined a point process on space X. So it was a random measure that is the mapping from probability space to space of counting measures. And I didn't prove enough, like I didn't give you a property how we can characterize or how we can define uniquely a point process. But if we consider the following so-called coincidence probabilities, so what are they? I will define the probability that at some subset A1 we can find exactly K1 points, at subset A2 we can find K2 points, and so on. So we can consider some subsets on our space, and if I will have such probabilities that we can find some number of points in different subsets, then actually such probabilities can define a point process on X. So I don't give here the proof because it's a little bit technical and not difficult. But the idea is the following. So if you know all such kind of probabilities, then you can uniquely define a point process. You can have here understanding or idea. This result is similar to that mm, cumulative distribution function uniquely determines distribution of random variable on R. So here the idea almost the same. Okay, so now for such coincidence probabilities, I will give some assumption. So like since in wave functions we had deal with densities of finding a particle in some subset. So here let us consider a simple case as well. So for simplicity, I consider space RD, and I will assume that we have following density for such probabilities. So here I have short notation. Here for each point x, I consider some small subset with size dx, so that this will be my plus dx1. I write like this. So, and if we consider different points, we will I consider such probabilities that in these small subsets we have exactly one point. This will be, for example, x2 plus dx2. So this probability, this limit means that this probability has density, and this density I denote by h m. So here, please notice that actually here from this definition we consider points that are not equal, because if we will have equal points, then it like we automatically get a coincidence density with index with lower index. And also the idea of these functions h, that they are actually probability densities that the process has m occurrences located in infinitesimal intervals xi plus or dxi. If we come back to example of a point process, and we recall that okay, if points are not equal, as we assume here, then from some moment these intervals are not intersected, and we know that for non-intersected subsets, the probability of Poisson point processes to find one point is equal are independent. So this probability will converge to a product of probabilities. So one can get that the coincidence probabilities for Poisson point process is equal to product of one-dimensional density. So we assume that we have a point process with intensity measure which have density rho, then we have this identity. So we will use it later, so don't forget these formulas that for Poisson point process we have a product of densities of intensity measure. Okay, so now if I will come back and find the connection with quantum physics, now I will try to define point processes such that their the coincidence densities has permanental structure or determinantal structure. So to do this, okay, I will take a symmetric non-negative defined function or C that acts from product of my space to R, and I will define a class of permanental point process where I just put I will assume that coincidence probability have density that can represent it in terms of permanent of this matrix. So for now, let us assume that they are exist. So because we don't know if they exist or not, uh, like we can define whatever we want, but the most important that we need to prove existence of such object. But for now, let us assume that such point processes exist. We will see the statement how we can prove existence of permanental point process. But for now, let us understand that we get what we want, that for a permanental point process, our particles will be somehow attract each other. Indeed, if we consider just two particles, so from definition of permanent, as I told you, the permanent of this matrix now for 2 points we will have matrix 2 by 2. These the elements of this matrix. So I'm sorry. So for permanent case, what we add products of diagonal plus products of element on anti-diagonal. And because of symmetricity, and one can notice that just one element is the coincidence probability for just for one particle. So this is H1 at point x1. This one is H1 at point x2, and this actually C square. So this here we add something non-negative. So this is less or not less than product of one-dimensional coincidence probability. In another interpretation, if I roughly write in terms of probabilities, what do I have from this density? So roughly writing the conditional probability that I can observe one particle in neighborhood of point x1 under conditions that I observe a particle in neighborhood of x2. So the conditional probability will be equal to to this value, and here from the previous from this line you can see that this is not less than a probability to observe the particle in neighborhood of position x1. So what does it mean? Like if I consider two positions x1 and x2, and I cannot see what is at x1, so I cannot see here. I cannot see just that at point x2 we can find a particle. So here I observe a particle. Okay, I for sure know that it is here. So this permanental structure of point process says that if I observe a particle here, then with higher probability I will find a particle here. Of course, a lot depends on the function c. So if you see here, usually covariance somehow depends on distance between x1 and x2. So if, for example, uh, x1 and x2 quite close, one to another, then this value we can try to make big. So you can say that yes, for sure, if you know that you find a particle here, then you can observe next to it with higher probability another particle. Of course, sometimes C for far distance between x1 and x2 almost zero, so like we can have some sort of independency if we try to say something about far locations, but if what we want to somehow guarantee that particles will group together somehow, uh, uh, form clusters. Okay, so indeed for permanental points process particles bunch together. Now in opposite case for determinantal point process, okay, everyone knows the how to find determinant of matrix. So we have the same calculation, but here with minus, and we have different the sign in another direction. So this means that quite opposite for the previous case. Like if we observe a particle here, if I know that it is here, then with lower probability, with the conditional to find a particle, I will say close to it, is lower if we don't have any information about location at x2. So this means that particles tends to repel each other. So if you see that I am sitting here, then I try to repel my neighbors, and function C2 will say how strong repelling or how weak it is. Okay, so now we somehow understand what kind of tools one can use if we want to construct or repelling or attracting points in point processes. And now let us move to next, and like I want to prove you that permanental point processes exist and we can construct them. Determinantal point processes also exist, and under general assumption on function C existence, you can prove you can get, but for permanental point process it's interesting because we can construct it using Poisson point process. It's interesting because, like we said yesterday, in Poisson point processes, points somehow independent one to another. But if we will assume that intensity measure for Poisson point process is random, then we will have a permanental point process, and it will have a bunching effect between points. But before starting to prove this, I need some technical tools how we can investigate point processes, uh, how we can use the coincidence probabilities that I defined. So I recall that the density of coincidence probability I denoted by HM, and you can find in literature that they have a lot of another names. So you can see that they're called M point densities. So this means that just as the density to find a probability at exactly m different points, or they call it correlation function of a point process. Uh, I will use sometimes this notation like m point densities. And I want to talk now about how we can use this endpoint densities to find higher moments of point processes. Yesterday we discussed that we have a very the first characteristic of a point process. It was a intensity measure which is equal to first moment of point process. Now, how we can calculate like second moments and so on. And it turns out that coincidence probability related to uh, higher moments of point processes. And to give an idea, I want to start to consider point process on Z. So in this case, it will be easier to understand, and we will not have some technical uh, details, but we will get an idea how one can proceed. So now I will consider a point process on Z, as I said, and I will assume that at each point I can observe at most one particle. So this means that each point of Z is empty, which is denoted as 0, or we have here a particle, and this means that measure of point x is equal to 1. So we have such a random combination of zeros and 1 on Z, but actually you can try to prove that the probabilities to observe just one particles can define a point process here. So you can define a distribution on infinite sequences, just knowing such probabilities that at point x1 and so on xn there is a one particle. So now if I will consider subset on Z. So for simplicity, I consider an interval. It can be any other subset. And I will sum coincidence probability for 2 points. And since I said that coincidence probabilities in this case are defined for non-equal points x, y, and xj, so I will write summation over non-equal points, and just simply taking summation outside of taking expectation outside of summation, I will write this sum of probabilities as follows. And so what I have the sum of indicators of points, or so I will count if I have a point and position xi where indices are not equal. And so now here, this is just notation for this measure. Let us see what is it. So like how we defined measure mu with brackets 2 of an interval. So since I define it as a sum of like I count particles which are not lying on a diagonal, so they are from interval I, but I did not add a particle that lies on the diagonal. So this means that if I count all particles on square and subtract the number of particles on diagonal, then I will have this summation. Another term, another notation, like I can rewrite this mu to with this 2 in brackets as such product. So I multiply number of particles in interval minus times the number of particles minus 1. So somehow it can recall you factorials of a number. So that's why we can give the following definition of a factorial n power of measure mu. So this factorial I will define on a product of the n power of our space. So we have just and for rectangulars of such form, I will put by definition the following. So I just do a product. I'm sorry. I make a product of values of number of particles in this subset, and I multiply them on 1 particle less, 2 particle less, and so on. And for disjoint subsets, if I consider a rectangular of diagonal that do not intersect diagonal of a product of space, then it will be just a product of number of particles here. Okay, so this is factorial power of measure, and as we started from a simple point process on Z, it can be proved that the expected value of factorial measure of subset B can be calculated as integral of endpoint density over subset B. So this is an important connection, how higher moments connected to density of coincidence probability, but sometimes, as you see, you can also interpret these densities as density of factorial moment of point process. So somehow in literature you can find this definition and then come back to coincidence probability, or how I define this is the same. Okay, now what is for Poisson point process? If you remember from course of probability, or you can try to calculate by yourself, if you have Poisson random variable, you can calculate that factorial product of this random variable is equal just to power of parameter of Poisson distribution. So here the same, if I have Poisson point process with intensity measure lambda with density rho, we can, I recall that coincidence density or endpoint density for Poisson point process is just a product of one-dimensional density. And this is just by definition, I'm sorry, this is by definition just usual power of intensity measure. So this means that for Poisson point process, moment of factorial product is equal to usual product of intensity measure. And it's quite useful in theory of Poisson point process. Okay, now we have all tools to try to prove, to construct the determinantal point determinantal point process. This is a case of symmetric wave function, so we will have some bunching effect in this point process. So as I said, we will use a Poisson point process, but we will try to define it with random intensity measure. These processes are known as Cox process. So Cox process is the Poisson point process with random intensity measure. So how to strictly define it? So first of all, we need to define the random measures on space X. Yesterday, we see how what kind of technical details we can deal with in order to define something random on space of measures. So now we want to define psi on to be mapping from omega to space of all measures. And I will not go to details here. I hope that you understand how to deal with it from previous lecture. And now if we have a random measure, so this means that here this measure depends on omega, and now you have just measure which indexed by random small omega. And using sigma algebra that's generated by random measure, I will define the Cox process described by its conditional probabilities. So I say that mu will be a point process such that a conditional probability to find in subset AI ki points is here I have just Poisson probabilities. So here I write for disjoint subsets. So here you can recognize density or the same probability for Poisson point process, but with difference that now here psi, this process measure psi is random. So if you define this conditional probabilities in follows, then you define a Cox process. Okay, so this we have such Cox process. Also, of course, one need to prove the existence of it, but let us assume that such a point process exists, you can just understand that what you need to construct first random measure, and then you construct independently Poisson point process with this intensity measure. And construction of Poisson point process we saw yesterday. Okay, now how to construct, I want to construct a permanental point process using this Cox processes. So for this, okay, you remember that in a permanental point process, to define it, we need to have a non-negative definite function which usually plays role of covariance function in quantum states. And so here I want to take this covariance function, and if I have a covariance function, so non-negative definite symmetric function, then I can find a centered Gaussian field on space X. We will work here on RD, but it can be done on more general spaces. But for simplicity, let us consider a Gaussian random field on RD. So this means that you indexed Gaussian random variables by point X from the space. And this means that for any collection of n points, the value of this Gaussian random field, so this is random variables that has a multivariate normal distribution. We assume that it is centered, so expected value of z of x is equal to 0. And we assume that covariance is given by this value. This is 1 over 2 covariance function k. So now what I will do, I will construct a random measure based on this Gaussian field. To do this, I take two independent random fields, Z1 and Z2, with the same distribution as Z here. And then I define a random measure in terms of this integral. So if I take B to be a subset on RD, I can integrate non-negative function here. Z1 square plus Z2 square I integrate, and integral will give you a measure which depend here on subset B. So you can see this is usual. You can define a measure with using of integral. Now I consider a Cox process directed by this random measured side. And it turns out that, I'm sorry, here mu, that this Cox process is a permanental point process with kernel K. This kernel K that I defined here, this means that the permanent in the formula of coincidence densities is equal to K. Like the permanent uses this function K. Okay, so let's try to prove. And again, proof is in general case is quite technical, but I want to give you an idea how to prove this. So let us denote the so-called density of our random measure. This is a random density by W. And now recall how endpoint density is connected to n factorial moments. So as I said, expected value of n factorial moments of point process can be calculated as integral over endpoint densities. And in order to prove that our point process is a permanental point process, we need to prove by definition that this density is represented as permanent of this form. So now let us understand what is endpoint densities for Cox process. And it's quite easy because we know that is conditionally Poisson point process, and for Poisson point process we have just products. So indeed, in order to find factorial moments of Cox process, I consider conditional expectation, and since so we have that mu is Poisson point process under condition psi. What we have here, as I told, we have just usual power of measure. So this is just a product of measures here. And from the definition of random measure psi, if I want to write a product of it, you can imagine that B is just a rectangular. So here is easy to imagine it, and then you will have just product of, okay, this is a density for psi, for random measure psi. So I just write the product of integrals over subset B. And now to put expected value inside, I can see that this is expected value of products of W of x1 and so on xn is my endpoint densities. And now we need to show that they can be represented as a permanent of a matrix of such a matrix. So here we should do some calculations. And calculations can be rather technical, but I want to show you, I'm sorry, here, I want to show you an idea. So how we can calculate the expected value of products of W of x1 and so on xn, but we will start for product of 2. So we have, let us find W of x times W of y and how to calculate expected value. So we will use here a Gaussian structure for this function W, and recall that it's represented as sum of squares of two independent Gaussian variables, and they identically distributed with one with that. So if I just write and simply calculation will give me that I will have two expected values of squares of z square of x, z square of y, and here these terms due to independency gives me just a product. So here I will have such an expression. I know that for process Z I have covariance function k, so the second moment is equal to k from xx over 2, and I have here 1 over 4. Now the idea is how to find expected value of squares of correlated Gaussian random variables, and Okay, here you can use different techniques. You can just try to calculate your joint density, but if you don't like to calculate integrals, we can uh, make such a trick. You can represent one Gaussian variables as a linear combination of another Gaussian plus something independent on z of y. So here this coefficient a, we choose such that it is equal correlation function of x and y divided by variance of at point y, and indeed you can find that expected value of z, and this part is equal to 0 just because how we defined this coefficient a. And from this you will have that this term is independent on z of y. So this approach can give you technique like you split your random Gaussian random variables to orthogonal parts, and now it's make simply the calculation, and indeed oh, if I substitute this linear representation for z square, you can get the expected value of squares of z of x, z of y. Like this is so simply algebra, and here we use independency. When I use independency, one terms this disappears because I have centered Gaussian variable, and here also because of independency we have product, and we can easily calculate. And well, you can double check my calculations, but what we have, if I have what I need, then we will do this calculation. Like I substitute now what I get to this formula, and indeed we got the following form, which is the permanent of this matrix. So I stop here because next step you can just use inductive step to prove that the product of n, like the w of x1 and so on, w of x n is equal to permanent, but the idea here, you can use this idea or some another calculations because you know actually the distribution of z. Okay, so here we constructed a point process with bunching effect. So you choosing correlation function k, you can make particles attract each other on some fixed radius with some fixed power. And what is more interesting here, that like in Poisson point process, particles were independent, but if you take their random intensity measure, then you will have some bunching effect in your particles. So this construction is for me quite interesting, and I think that we use here today we use a new tool for investigation point process, and we construct a point process with some properties that we want. Okay, so this all for today's lecture. If you have questions, remarks, you can ask. Okay, if no questions, then for today, uh, that's all. We had 3 lectures, and today, I'm sorry, tomorrow, we will start as usual at 3 by Beijing time. So please come. We will have 2 lectures tomorrow. So see you tomorrow.